Hello and clear skies, everyone, and welcome to York Observatory TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Quinton, and I'm joined tonight by Gagan, Amin, and Matt. We are broadcasting live from the Alan I. Carswell Observatory, located at York University in Toronto, Ontario, Canada. York TeleTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time, but if you can't make it to one of our broadcasts, don't worry. All of our TeleTube events are recorded and uploaded to our YouTube channel for you to watch at whatever time works for you. If you have any questions about the material covered in tonight's show, please feel free to ask them in the live chat, and we will try our very best to answer them over the course of the night. If you have any questions or comments about our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on Twitter or Instagram with the handle @YorkObservatory and on Facebook at Alan I. Carswell OBS. And we have a special announcement tonight. Observatory calendars and postcards are available for the first time ever as online purchases. So if you would like your own personal copies of some of our best astrophotography images, please feel free to check out our merch. You can visit our website at observatory.info.yorku.ca to find out more. I'll be handing the mic over to the main speakers to get the show started in just a moment, but before I do, I want to take a bit of time to let you know what celestial objects you can observe for yourself this week. Mars continues to appear very bright in the night sky. It will be visible from sunset to around 3 a.m., making its way from east to west over the course of the night. If you happen to be able to watch the skies right now, you should be able to see it in the southwest, just above the moon. Mars and the moon will remain quite close together all night tonight, so it should be easy to find no matter what time of night you want to observe at. The moon is currently in a waxing gibbous phase and will remain so until we reach a full moon on the night of November 29th and the night of November 30th. At this point, the moon will also be passing through the Earth's penumbra, allowing residents of North and South America, Australia, and parts of Asia to see about 82% of the full moon turn a bit darker. Also visible in the sky is the bright light of Jupiter and the dimmer light of Saturn, sitting right next to each other in the southwestern sky. The two gas giants are visible from sunset until around 8:30 p.m. Jupiter and Saturn are practically right on top of each other in the sky right now, and will only get closer and closer as we approach the Great Conjunction on December 21st. All of these objects are visible with the naked eye alone, but if you have a telescope, even a small one, you should be able to make out features on the surface of Mars, the rings of Saturn, and the bands of Jupiter, as well as its 4 Galilean moons. This time of year is an excellent time to observe the Pleiades, as they will be visible in the sky all night long. The Pleiades are an open star cluster in the constellation of Taurus, appearing to the naked eye as a collection of 7 or so stars located very close together. However, if you have a telescope and live in an area with sufficiently low ambient light, you may be able to see that the cluster actually contains many more stars than this, over 1,000 in fact. Now that you've gotten a taste for some of the celestial objects you will be able to observe this week, it's time to continue on to the main event. I'll now hand the mic over to Gagan to introduce you to tonight's main topic, the moons of the solar system.
Thanks, Quinton. Good evening, everyone. I'm Gagan, and I'm here with Quinton, Amin, and Matt from the Alan I. Carswell Observatory, and today we'll be talking about moons of our solar system. Let's get started with a bit of background and history. What is a moon? A moon, or natural satellite, is a body orbiting around a planet or dwarf planet. The moons in our solar system vary greatly in shape, size, and composition. Pretty much any astronomical body orbiting a planet or dwarf planet, or even an asteroid, can be considered a moon. The first moon ever discovered was, you guessed it, our moon. But with hundreds of moons in our solar system, let's see how early research started. In 1610, Galileo discovered the first natural satellites of another planet. These were Jupiter's largest moons, Io, Europa, Ganymede, and Callisto. These 4 moons are therefore called Jupiter's Galilean satellites. Interestingly, Galileo initially referred to these moons as planets revolving around Jupiter, and later actually named his discovery as stars. The name moon was only used to refer to our moon and later on in solar system studies. But to differentiate our moon from other moons, a natural satellite is a more common designation for moons around other planets in our solar system. The terms moon and natural satellite can be used interchangeably. There are a few different methods to how moons can form around planets. The first way is the giant impact hypothesis. This is the most widely recognized theory for how our moon formed, and Amin will be going into more detail about it in a few minutes. This hypothesis is also applicable to the dwarf planet Pluto's moon, Charon. The other ways that moons can form in our solar system are formation through the circumplanetary disk or through capture. During planet formation, the circumplanetary disk is the disk of matter that revolves around a planet. This disk can contain dust, gas, planet-like masses, and asteroids or fragments. In the image on the left, a circumplanetary disk can be seen in red around an exoplanet PDS-70c. Matter in the circumplanetary disk can eventually accrete to form a moon or ring system. Natural satellites that are generally more round and regular in shape, or have reached hydrostatic equilibrium at some point in their histories, are more likely to have formed through collapse or accretion of matter in the circumplanetary disk. Some are actually classified as planet-sized moons, and Jupiter's moon Ganymede and Saturn's moon Titan are both bigger than the planet Mercury. These moons also orbit closer to their host planet and have less eccentric and less inclined orbits. This means that their orbits around their planet are more circular and the moons usually orbit on a flat plane. In general, moons formed during planet formation through the circumplanetary disk are called regular moons. Another possible way for a planet to get a moon is for it to capture one. Moon capture is when a planet's gravitational force causes it to capture a nearby or passing body, such as an asteroid or planetesimal. This method of moon formation is common with smaller and more irregularly shaped moons. Their orbits are usually wider and more eccentric than those of moons formed through the circumplanetary disk, and can be more inclined compared to the planet's plane of rotation. Natural satellites that were captured and retained in a planet's orbit are often referred to as irregular moons. Moons like this includes Mars moons Phobos and Deimos, which are captured asteroids and still retain their potato shapes even in orbit around Mars. One interesting outlier of a captured moon is Neptune's moon Triton. Triton is believed to be a captured dwarf planet or planetesimal due to the retrograde and inclined nature of its orbit, as you can see in the diagram below. Triton is slightly larger than Pluto in size and has a very similar composition, and therefore probably originated in the Kuiper Belt. Triton was likely originally part of a binary dwarf planet system, similar to many Kuiper Belt dwarf planets, and during their interaction with Neptune, Triton was retained in orbit while its companion was ejected. This hypothesis of object capture from a binary system is also plausible for Mars' moons and several other solar system moons. In our solar system, almost 200 natural satellite moons exist around the core 8 planets, with the exception of Mercury and Venus. Saturn is home to the solar system's largest moon system, with 82 moons. At a close second place, Jupiter has 79 moons, followed by Uranus with 27 and Neptune with 14. For the giant planets, new minor moons are being discovered relatively often thanks to surveillance and ongoing research. Beyond the gas giants, though, hundreds more dwarf planets are confirmed to have natural satellites orbiting them, and some even with multiple. Pluto, for instance, has 5 natural satellites orbiting it. Small moons around planets or dwarf planets, and sometimes even asteroids, are called minor satellites, or affectionately, moonlets. Oftentimes, moonlets can be small bodies that orbit their host planet while embedded in their ring system. Another hypothetical type of moon is a subsatellite, which is a natural satellite orbiting another moon. In simulations of our solar system, these are predicted to occur quite frequently, yet there is no recorded instance of a confirmed subsatellite. Subsatellites also have a funny nickname which I absolutely love. They are sometimes called moons. Now that you're all familiar with what moons are and different types of moons, I'll pass the mic over to Amin, who will be teaching you all about our very own moon.
The moon is Earth's only natural satellite, although there are some other near-Earth objects that come into orbital resonance with Earth which will not be mentioned in this talk. The moon is rounded due to its gravity. It has a mean radius of 1,737.4 kilometers, which is almost one-third of Earth's radius. This is quite unusual because most moons are much smaller than their planets in terms of radius. Its mass is 7.342 times 10 to the 22 kilograms, which is a number with 23 digits. This mass is comparatively much smaller than Earth's mass because the moon's density is lower. The moon has no atmosphere, hydrosphere, or magnetic field. Some of the most abundant chemicals on the lunar surface are oxygen, iron, and silicon. The oxygen is not in gas form, but is part of other chemicals within a compound, such as iron oxide or rust. There are other metals as well, such as magnesium, calcium, aluminum, and titanium. Carbon and nitrogen are very low in abundance. The surface is heavily cratered, and these surface features remain etched indefinitely because there is no erosion from any atmosphere or plate tectonic effects which change the surface. There cannot be liquid water because of solar radiation. The moon is thought to have been formed around 4.51 billion years ago, which is relatively not long after the Earth itself formed. The main theory of how the moon forms is that a Mars-sized object called Theia collided with the Earth. Theia may have been another planet from the early solar system. After this hypothetical collision, pieces of both Earth and Theia would have been ejected into space and would have eventually formed the moon. The moon has distinct regions of the crust, the mantle, and the core. The inner core is solid and iron-rich, while the outer core is fluid. The mantle is partially molten, and the crust is obviously solid. Only one face of the moon is ever shown to the Earth. The far side, as it is called, has a thicker crust, which is probably because the moon was created from two different bodies that fused together. The collision theory of the moon's formation is supported by the fact that rocks on the moon and on Earth seem to have similar signature features. The collision that is thought to have created the moon is also thought to have caused the Earth's 23.5-degree tilt, which then allowed for the seasons to come into being. Other theories also exist. For example, that the moon was captured by the Earth, that the Earth released some mass on its own to space due to its initial rapid spin, or that the Earth and the moon formed jointly from the materials present in the early solar system. The moon causes tides on Earth. These result from differential gravitational forces, meaning that some parts of the Earth feel stronger gravitational forces from the moon than others, causing bulges in bodies of water. Tides are thought to have played a role in the development of life on Earth. The moon is currently moving away from the Earth at a rate of 3.78 centimeters per year. Next, I will discuss specific lunar surface features. As seen in the picture in this slide, there is a clear contrast between the bright and dark areas of the moon. The lighter areas are called the lunar highlands, which are made of anorthosite rock, while the darker areas are called Maria, which are made of basalt. Anorthosite and basalt are also seen on Earth. They are igneous rocks, meaning they were created by cooling magma. It is not completely known how anorthosite forms, so more research is needed to find out how the moon has so much of it. Maria means seas in Latin, and the name was first used for the moon by Johannes Kepler in the 17th century. The lighter highlands are older than the darker Maria, and are thus more heavily cratered. The Maria came about from volcanic processes on the moon, and covers 16% of the lunar surface. Lava flow patterns can be seen in the Maria, which confirms their origin. Rills and dome features give evidence of volcanoes. Wrinkle ridges and grabens are structures that show tectonic forces are also at play. Radiometric dating established that the Maria are a few billion years old. Impact craters are the most notable of the moon's geological features. They are formed when a solid body, such as an asteroid or a comet, collides with the surface at high velocity. The average velocity of such impacts has been determined to be 17 kilometers per second. Crater sizes have been decreasing over time. Older craters are larger than newer ones. Craters are usually very circular instead of irregularly shaped. This is interesting because the impacting objects are mostly never perfectly circular. Craters are round because the material from the impact spreads out in all directions in a shock wave. This is due to the large kinetic energy of the object, which is released in a circle. Objects often strike Earth as well. So where did Earth's craters go? On the Earth, erosion, for example, due to weather, water, plants, etc., plate tectonic effects, and volcanoes are rampant due to various geological processes. These processes eventually erase craters after they form. The moon is relatively dead when it comes to geological processes, and so once a crater forms, it will remain there for a long time. The moon also contains valleys, and mountains. There are 12 named valleys, most of which are named after a nearby major crater. There are many more named mountains and mountain ranges. The tallest mountain is called Mons Huygens. It was named after the Dutch astronomer, mathematician, and physician Christian Huygens. Its elevation is 5.5 kilometers. It is not, however, the highest point on the Moon. That would be the Selenian summit, which is 10.786 kilometers above the average lunar surface height. This summit is on the far side of the Moon, and is comparatively taller than the Earth's highest point, Mount Everest, taking into account sea level as the average height on Earth. Other named features of the Moon include Dorsa, Promontoria, Rimae, Rupes, and Terrae. The aforementioned lava flows play a major part in creating some of these surface features. To conclude the section on the Moon, we will discuss internal structure. The Moon has a mean density of 3,346 kilograms per cubic meter. This means that it is probably mostly rocky and poor in metal content. The crust, mantle, and core stratification, which we discussed earlier, is thought to have been created after the fractional crystallization of a large magma ocean, which existed shortly after the Moon was created. The energy that melted the molten areas of the interior of the Moon came from the impact that created the Moon. Seismometers left behind from the Apollo missions discovered the internal structure. The crust is thought to be 50 kilometers thick on average, although in some places it may be 15 kilometers more or less than that. Moonquakes have been detected deep in the mantle, around 1,000 kilometers under the surface. Some shallower quakes have also been found at a 100-kilometer depth. Because of the lack of a rotating molten iron layer like on Earth, the Moon has only a very weak magnetic field. This is called the dynamo effect, which the Moon does not have. The core of the Moon is very small compared to the cores of other celestial bodies. Its radius is only around 350 kilometers. And now Matt will be speaking on moons of other planets in the solar system. Go ahead, Matt.
Thank you, Amin. And yes, in fact, our solar system has a lot of interesting moons. Sadly, I guess it would take a really long time if we talk about each of the moons found in our solar system, since there are more than 200 of them. Therefore, I'm only going to cover a few of them because of their special characteristics, ones that could even help us look for potentially habitable planets elsewhere in our solar system. That being said, or places in this case, that being said, I think we should start with Jupiter. Jupiter has a total of 79 moons, and some of them are really special due to their composition, presence of water, high volcanic activity, and other interesting details about them. The most important ones are known as the Galilean moons mentioned before. We start in this case with Io. With its peculiar pizza-like surface, it's slightly larger than our own moon, making it the fourth largest of the solar system. It has the peculiar characteristic, which is also the reason why its surface looks so bizarre, that it is the most volcanically active object in our solar system, with more than 400 active volcanoes. The reason for this to happen is tidal heating, due to Jupiter's massive gravitational pull, as well as the pulls from Europa and Ganymede. Unlike most moons in the outer solar system, which are mostly composed of water ice, Io is primarily composed of silicate rocks surrounding a molten iron sulfide core, and most of Io's surface is composed of extensive plains with a frosty coating of sulfur and sulfur dioxide, which is also the main constituent for its very thin atmosphere. We continue with another of Jupiter's moons, Europa. It may be the most promising place in our solar system to find present-day environments suitable for some form of life beyond Earth. Slightly smaller than Earth's moon, Europa's water ice surface is crisscrossed by long linear features, cracks, ridges, and bends. The moon's ice shell is probably 15 to 25 kilometers thick, beneath which it is believed there is an ocean of liquid salt water 60 to 150 kilometers deep, which would be as twice as much water as all the water in our oceans combined. And the fact that it remains liquid has the same explanation as what happens in Io. In other words, it is mainly caused by tidal heating or tidal flexing. Like Earth, Europa is thought to also contain a rocky mantle and iron core, and abundant liquid water and energy and the right chemical elements make Europa one of the best places in the solar system to seek present day life beyond Earth. Observations with the Goddard high-resolution spectrograph of the Hubble Space Telescope revealed that Europa has a thin atmosphere composed mostly of molecular oxygen and some water vapor. This does not mean humans can breathe and live there without a spacesuit, though, because we are talking about an extremely thin atmosphere. I'm sorry. Another of the Galilean moons, Callisto, is Jupiter's second largest moon and the third largest moon in our solar system. Its surface is the most heavily crater of any object in our solar system, which also means there is little to no geological activity on this moon. It has an icy surface covered by craters of various shape and sizes, including bowl-shaped craters and craters with multiple rings. Data gathered by the Galileo spacecraft indicate Callisto may have a subsurface ocean, and scientists estimate it may be 250 kilometers below the surface. If there is an ocean, it may be interacting with rocks, giving Callisto the chance of supporting life. Callisto's interior may have layers of ice mixed with rock and metal, possibly extending to its center. And NASA's Galileo spacecraft detected that Callisto contains a thin carbon dioxide atmosphere or exosphere, but later research determined Callisto also has hydrogen and oxygen in its atmosphere. The last Galilean moon and the largest of them all, Ganymede. It is the largest moon in our solar system, and in fact, it is larger than Mercury and Pluto, and slightly smaller than Mars. And it is also the only moon with its own magnetic field, which also causes it to have auroras, just like we see on Earth's poles. Ganymede has large, bright regions of ridges and grooves that slice across older and darker terrains. These grooved regions are a clue that the moon experienced dramatic upheavals in the distant past. Scientists have also found the strong evidence of an underground ocean on Ganymede. It also has a thin oxygen atmosphere like Europa's, but there isn't a high chance that it holds life due to the fact that it is believed that the pressure at the base of the ocean is so high that any water down there would turn to ice. This would make it difficult for any hot water vents to bring nutrients into the ocean, making it almost impossible for its oceans to harbor life in any form. There is one moon that may not necessarily have oceans of liquid water, but liquid methane, as well as a substantial atmosphere like Earth's, Titan. So far, Titan is the only place besides Earth known to have liquids in the form of rivers, lakes, and seas, not below the surface like on Callisto or Europa, but on its surface. Titan is larger than the planet Mercury and is the second largest moon in our solar system. Jupiter's moon Ganymede is just a little bit larger by about 2%. Titan's atmosphere is made mostly of nitrogen like Earth's, but with a surface pressure 50% higher than Earth's. Titan has clouds, rain, rivers, lakes, and seas of liquid hydrocarbons like methane and ethane. The largest seas are hundreds of meters deep and hundreds of kilometers wide. And beneath Titan's thick crust of water ice, it is believed that there could be more liquid, an ocean primarily made up of water rather than methane like we saw on the other moons. Titan's subsurface water could be a place to harbor life as we know it, while its surface lakes and seas of liquid hydrocarbons could conceivably harbor life that uses different chemistry than we're used to, or no life at all. Last but not least is another one of Saturn's moons, Enceladus. Not only does it have the most reflective surface in the solar system because of its fresh, clean ice due to water volcanism, but it is also seen as an ocean world because its surface is made up of almost entirely of water ice, and it is an active moon that hides a global ocean of liquid salty water beneath its crust. What's more, jets of icy particles from that ocean, laced with a brew of water and simple organic materials, gush out into space continuously from this fascinating moon. The material shoots out at about 400 meters per second and forms a plume that extends hundreds of kilometers into space. Some of the material falls back onto Enceladus and some escapes to form Saturn's vast E-ring. Samples have been taken from these, and scientists have determined that Enceladus has most of the chemical ingredients needed for life, and likely has hydrothermal vents spewing out hot, mineral-rich water into its ocean. After hearing about all these moons, We would like to ask you, to which of these moons would you like to go and why? And also, if you think that there could be a form of life present on these moons. With this, we conclude our presentation about the moons on our solar system, and we'll be here for any questions you may have. Well, everyone, you have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Quinton, Gagan, Amin, and myself, Matt. As I mentioned before, make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation or purchase a calendar or postcard, please see our website at observatory.info.yorku.ca. And you can always connect with us on Twitter with the handle at York Observatory and check out our website for show notes, content, updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in. Clear skies and have a good night.